Okay, so what is a sparse matrix? Well, I don't know if I've seen like a great mathematical definition for a sparse matrix. For the stuff that we're doing in this class, the idea is that if we have a sequence of matrices, like if we have matrices corresponding to a discretization of a PDE or something like that, if we take more and more grid points, if we make the mesh finer and finer, the idea is that the ratio of non-zero entries in the matrix should go to zero. And there should be a very few number of zero entries. Now, why do we care about this? So I'm just going to sort of briefly explain why we care about some of these things. If you have a large system of equations that we want to solve, and the only thing that we know about our matrix is that it is an M by M matrix, then standard Gaussian elimination and other, its other variants takes roughly O, big O of M cubed operations. Okay, now the best way in this case to understand what O of M cubed means is the following. If M doubles, the runtime increases by approximately by a factor of approximately 2 cubed, which is equal to 8. So if we have M, if we go from an M by M matrix to a 2M by 2M matrix, the runtime is going to roughly increase by a factor of 8. In other words, it's not simply going to double. Okay, so let's think about how this works in our PDE example. So in our PDE example, if we have n unknowns, then M, if we're in one dimension, if we have n unknowns, okay, so typically typically the way that we use n, there would be n minus 1 unknowns, but let's just say we have n unknowns. For one dimension, the matrix is an n by n matrix. So what does this mean? It means if we need to make our grid, if we need to half the size of our if we need to take our mesh and make it finer, make it twice as fine. In other words, instead of n, we'd have 2n unknowns. Then the runtime is going to be 8 times what it was before. Okay, because n unknowns leads to an n by n matrix. Okay, what about if we are in 2 dimensions? So let's say we're in 2 dimensions, and each interval. So let me maybe say it like this: in 2 dimensions. Actually, let me back it up to make this a little more consistent. If there are n subintervals, in a 1D discretization, the matrix is an n by 1 by n by 1 matrix. And so if we go from n subintervals to 2n subintervals, the runtime is going to increase by approximately a factor of 8. Because that's, n is going to go from n minus 1 is going to be 2n minus 1, and so we're going to get a runtime that increases roughly by a factor of 8. Okay, but notice what happens in 2D. In 2D, if we divide the x and the y axis up into n subintervals, we're going to have an n minus 1 squared by an n minus 1 squared matrix. So now if we double in, the size of the matrix is roughly going to be 4n by 4n. Whoops. So if you have an n minus 1 squared by n minus 1 squared, if we have n subintervals in 2 dimensions, n subintervals in the x direction, and in subintervals in the right direction, we're going to have an n minus 1 squared by n minus 1 squared matrix. Okay, so if we double that, we're going to have a matrix that is roughly, not roughly, it'll be exactly 2n minus 1 squared by 2n minus 1 squared. And now this is roughly going to be a 4n squared by a 4n squared matrix. And so now what is the difference between the runtime of this matrix and this matrix? It's not going to be 2 cubed, it's going to be 4 cubed. Okay, so you can see what's happening now. Instead of being 4 to the power of 3, it's going to be, instead of being 2 to the power of 3, it's going to be 4 to the power of 3, which is 2 to the power of 6. And in 3 dimensions, it's not going to be that. It's going to be 8 to the power of 3, or 2 to the power of 9. So what this means is if we have a problem that we want to, if we have a PD that we want to discretize in 2 dimensions, and then we want to just refine the mesh so that we have twice as many subintervals on the x-axis and the y-axis, the runtime to do that refinement, the runtime is going to increase not by a factor of 2, not by a factor of 4, not by a factor of 8, but by a factor of 2 to the power of 6, which is 2, 4, 8, 16, 32, 64. So the runtime is going to increase by a factor of 64. And if we're in 3 dimensions, the runtime is going to increase by a factor of roughly 512. Okay, so then what this is saying is that if Gaussian elimination is the only algorithm that we have, it might become the case that very quickly our systems are too large for us to practically be able to solve using Gaussian elimination. So this is where sparse matrices come in. So, like I said, a sparse matrix really just means a matrix where most of the zeros are entry, or most of the entries are 0. Now, I've mentioned before that in some special cases, like if the matrix has a very nice form, like a tridiagonal form, this is the sort of thing that we get when just modeling Poisson's equation, like just Poisson's equation, not Poisson's equation with some other like transport term or something like that. Okay, in those cases, there are extraordinarily fast solvers, like the Thomas algorithm and its variants will solve a tridiagonal system. We'll solve a tridiagonal n by n system in roughly O of n steps. So in other words, if you double the size of the grid, the runtime doubles, exactly kind of like you want it to. So to the best case scenario. Okay, but if you don't have a system like that, but you do have a system that is nevertheless sparse. So a tridiagonal system is sparse. If you have a system that is not like that, but it's still a sparse system, then what you can do is you can do matrix vector, you can write algorithms to do matrix vector multiplication very quickly. Now, typically, if you have an n by n matrix and an n-dimensional vector, matrix multiplication is going to cost about n squared. It's going to take about n squared time. Meaning, if you double the size of the matrix and the vector, the time to do the matrix vector multiplication is going to increase by a factor of 4. Or if you multiply by 10, so maybe go from a mesh size of 0.1 to a mesh size of 0.01 or something like that, the matrix multiplication is going to increase by a factor of 100. Okay, and this is one of the things in this week's homework that you're going to see that you're going to experiment with. And we've already had some experimentation with this. But now, on the other hand, if we have a sparse matrix and most of the entries are non-zero, then we don't need to do actually n squared operations because there's far fewer non-zero entries. So for the matrices that we're looking at in this class, they're all going to be banded matrices with at most like 5 non-zero bands. So we can have a matrix that's 10 million by 10 million, but there's only going to be at most 5 non-zero bands for the matrices that we're looking at in this class. So therefore, what this really means is that we should be able to come up with an algorithm that does matrix vector multiplication not in n squared time, but in basically the number of bands times n time. So for example, if we have an n by n matrix that has 5 bands, then to do matrix vector multiplication, there should be a sparse algorithm to do that, such that when you double the size of the matrix, the runtime of the algorithm only doubles. It doesn't go up by a factor of 4. Okay, there should be an algorithm that does that, and that is one of the things that you're going to do this week in your homework. Okay, there's a challenge. I'm going to sort of walk you through one way to do it that I think is maybe the simplest and most naive, but is also much slower than something that you can do otherwise. Okay, for those of you who kind of like thinking about this and making something go faster and faster, I think you'll get a kick out of it. And if not, you'll be able to at least do the first part pretty clearly. I'll show you what to do, and then you can compare yours with sort of the naive matrix vector multiplication. Anyways, so this is the idea of sparse matrices, is that we can do matrix vector multiplication in constant time. That is, it's just not constant time, in time that is linearly proportional to the size of the matrix. Meaning, the way I like to think about this is if we double the size of the matrix, the runtime only doubles, rather than going up by a factor of 8 or 64 or something like that. Okay, so that's great, but how does that help us in this class? Well, what we are going to see is that we are going to be able to do matrix vector multiplication over and over again many times, and it's going to give us a way to solve the system of equations. Now, the downside is that the number of times that we have to do matrix vector multiplication is going to depend on like the size of the matrix. Okay, so as we will see, we're going to show, and this is going to be more when we analyze the algorithms in week 4. We're going to show that yes, for an n by n matrix, we can do a matrix vector multiplication in roughly n operations. But we're going to show that we need to do a lot of operations, and so we'll analyze the algorithms there. But it's still, for what we're going to see, it's still going to be better than what you would do with just a straight Gaussian elimination algorithm. Okay. Now there's other sparse solvers as well that can quickly solve a banded matrix in much fewer iterations than Gauss-Jordan. So there are banded solvers that can solve the sort of banded matrices that we're going to look at, and it would be able to solve those in roughly the same amount of time that we're going to be able to solve it in the methods that we're learning this week. However, we're going to learn more methods. We're going to be learning more methods after this week, and I think it's a strength of the iterative methods that with such simple methods, we can beat, in some sense, these very advanced algorithms. Now, please understand, it's not that very advanced algorithms don't have a point. In fact, in many cases, they can be more useful than the algorithms that we're going to use. And the reason is because in these algorithms that can solve banded matrices, or that they can quickly compute solutions to equations where the matrix is a big banded matrix, what it really does is compute the LU factorization. Once you have the LU factorization of the matrix, you can solve the corresponding system of equations very quickly in linear time. Okay, well, this is good in practice because that lets you basically spend a lot of time solving one system of equations, but then you can actually use that same LU factorization for different right-hand sides. But you can't do that with iterative methods. So I don't want to sound like an arrogant jerk here that's saying iterative methods are better than these other things. I'm just saying there are times when iterative methods are the only practical thing to do. There are times when non-iterative methods are the only practical things to do. And then there's this big, sort of in the middle area where it depends on what the exact application is. Sometimes iterative methods are practical but not the best, and sometimes a direct solver is practical but not the best. But the thing that I want you to get from this video, and really all we're going to talk about for now about chapter 3, is that sparse matrices are good because we can, I didn't even mention this, we can store them very inexpensively, and we can do matrix vector multiplication very quickly. And that is, both of those things are things that are needed to make iterative methods feasible because we have to do computations over and over again and store a lot of matrices.